Recording is rolling. So welcome to Thursday. Guest number that yesterday, today, just want to cover a bunch of electromagnetic spectrum and optics demos with you guys. Got a bunch of new posters up here. This is my very ambitious list. So I hope you get through all this today, but we're going to find out. Here's top scientist for last quiz. So you guys are doing awesome. This is great. I do still have quite a few students who haven't turned in the quiz yet. I do want to get those on before I pass them back. I've got the solutions ready to go. So, just to be fair to everybody. But yeah, you guys are doing really awesome. You guys are a great class. So let's get to see item 1 on this list. Actually, this first one, I think I accidentally missed with you guys yesterday. Did I tell you guys about whispering dishes? Okay, let me switch the screen over. Whispering dishes. Hang on. All right, so.
Oh yeah, I have one. Why not?
All right, here we go. How many guys have ever seen any of these around out in the wild? Maybe someone looks like this guy right here, like a pair of these dishes that are aimed towards each other. You guys ever seen one like this? If you ever do, and I do know where one pair of these dishes is if you ever go to University of Florida up in Gainesville, and you happen to be at the physics building, in the lobby of that physics building are a bunch of really cool physics demos, including a pair of these across the lobby. So you guys remember yesterday doing those reflecting mirrors, reflecting concave mirrors? I remember the pig in the flying saucer. Okay? So this is that shape, isn't it? Except these don't reflect. It's not light that you care about. It's sound. So sometimes these are called acoustic mirrors. Okay? And if you put your ear at your ear at the focal point of one of these, and so your friend on the other side is speaking, even in a whisper, also at the focal point. So now if you speak in a whisper, people a couple meters away shouldn't be able to hear you. But that sound gets redirected, reflected all the way to the other side, and you can actually pick up and hear on the other side, even though the person is whispering on the other end. Hear it really well. This is related to this idea called a whispering gallery. Now, a lot of these whispering galleries are created completely by accident, but a lot of buildings that have some kind of elliptical shape to them, there's a natural acoustic mirror effect set up. So you can stand at one place and hear a conversation that somebody's having very quietly on the other side of the room. There's a whole list of these. A lot of these are legislative buildings, funnily enough. So if you're like a legislator, you can spy in on your colleagues, hear what they're saying. All right, so let's see about that. All right. Then what we were doing was I wanted to use Paul Hewitt's textbook as a checklist because, again, I'm trying to give you guys just a real broad overview, show you guys a bunch of stuff that you wouldn't learn otherwise. And then if you see something that intrigues you, you're like, oh yeah, go home and Google this and learn about it a little bit more. So I told you guys about reflection yesterday and also refraction, Snell's law, the whole deal. We did ray diagrams, we did equations. Then if you take those two effects together, you can explain rainbows. Right? So a rainbow, whenever you see a rainbow, the sun is always behind you, and the rainbow is always at like a 40 to 42 degree angle from like your line of sight between the sun behind you and you. Right? Now, why is that? Well, where does rainbow come from? Well, it has to do with reflection and refraction working together through water droplets. So, I mean, it usually happens after rain, right? It's really humid outside. So you've got all these water droplets in the air, got some ray of light. And remember how light refracts at different wavelengths of light refract at different angles, like the whole prism with the colors spreading out. Isaac Newton figured out, put all the colors together to get white light again. Right? So that's why the colors spread out. That's why you get the rainbow effect. But part of this too, this has to do with the sunlight being behind you, but you see the rainbow in front of you, has to do with total internal reflection. Remember, any material that's transparent has some index of refraction, and there's some associated critical angle, and there's a point where there will be no refraction, and you'll get total internal reflection. So put those two ideas together, you get that. Let's go down here. All right, then, speaking of which, total internal reflection. I think I showed you guys this yesterday, or something similar to this, but here's a Paul Hewitt animation version. So you shine a light, it'll refract coming out of the water. But see, at some point, this refraction angle from this normal line would approach 90 degrees, so it doesn't refract anymore. You get total internal reflection. So if you're like a fisherman up here in a boat and you're looking down trying to see this fish, well, you wouldn't be able to because none of the light information even leaves like at this point. So if you're in a boat right here, forget, you'll never see it. Okay. Let's go lenses. Okay, so lenses involve refraction, like Snell's law. You guys remember Snell's law yesterday? We did a quick Snell's law demo for this prism. Remember, we figured out the index of refraction was about 1.5, which means that light slows down by about 50% inside. Hold on, wow. Yeah. Here, draw that layout formula. So index of refraction is speed of light in a vacuum compared to speed of light in the material. So that ratio was a 1.5 ratio approximately for it. And we figured that out going through Snell's law. Right now, if you have that and you turn this into a lens, you can get these interesting refraction results. Maybe like a magnifying glass. Maybe this might be how a magnifying glass would work. Now, some of this magnifying glass somehow, and there's an image of a candle showing upside down, right? Or you could use magnifying glass to like magnify. Right? What would the differences in those be? Well, the refraction rules are similar to reflection rules in a way. So there could be a ray of light that, say, like parallel to the ground. You guys remember these ray diagrams yesterday we were looking at? But reflection would like a point bounce out to the left. But refraction, we're interested in light that refracts through, and then look, double focal point, because light can go right to left or left to right. So it's going to refract through this focal point. There's always also a ray of light that goes straight through the middle. Now maybe refracts a little bit here, but negligible amount. Right. So just draw a line. Okay. And then where they converge on the other side, that would be where the image is. Oh, hey, look, it could be like upside down, kind of like this picture right here. Okay. Now, look at where the object is though. See how it's outside the focal distance? Okay. What if you instead had the object inside the focal length? Okay. So this object's inside the focal length, okay. And you're like looking from this side. See, like there's an eyeball right here, like looking here. Okay. Do the same refraction rules, the image is going to appear to be blown up really big. Like it's been magnified, right? And the definition of magnification is this height compared to this height. You just divide the two, right? Yeah. Okay, so if you're ever trying to magnify something with magnifying glass, then make sure that the object is inside the focal length of the magnifying glass. Because if it gets out too far, well, here's a bunch of different scenarios you could have with the same lens, right? The same magnifying glass. Okay? Here's where's it? Well, okay, the one's actually magnifying is just right here. That's the only one. Okay. But then these other ones, you get like these inverted images, right? Just like you saw back here, this one. And this top one is actually kind of interesting. What if you have an object right at the focal point? Well, the rays of light would actually be parallel to each other after they've refracted. Or if you turn that around, say you had parallel rays of light coming from like infinitely far away, they would converge to the same point on the focal point. If you've ever taken a magnifying glass and like try to burn leaves or something with it, like there's some distance you have to hold, but that'd be the focal length, wouldn't it? Where all the light rays converge at one point. Okay. So we got, okay, we got a diverging lens, right? So here's the object, here's an image that's smaller, right? For diverging lens. If you are nearsighted, then your glasses look more like these converging lenses. And if you're farsighted, then you might wear glasses that look more like this diverging type lens. Common optical instruments, I've got camera, telescope, telescope and compound microscope. These are really similar type technologies. Okay, so let's take a look at one of these. It'll zoom in on the telescope here. Where you might have maybe a couple of lenses, an objective lens and an eyepiece lens. Now, what's the advantage of this? Well, you get like a double magnification. So here's light coming in from like infinitely far away or extremely far away, parallel rays. It's going to converge and create like an image here. And then if you align the focal lengths of these two lenses, then that image could be magnified again, and then it would appear like super big. Right? So something that would be small would be blown so big. Compound microscope, really similar idea. Right? Trying to take this little tiny object and blow it real big where you can see it. Got an object lens and an eyepiece, projector, similar idea. It is strikes your interest, and you can well, you know what to look for if you want to Google any of this stuff. Okay, so we got eyes are actually lenses also. Eyes are refracting lenses. And, you know, like this, if you are nearsighted, then well, if you have a like normal vision, then the light should converge on the back of your eye, the retina, and that information goes to your brain and hopefully you get like 20/20 vision or better. If you are farsighted, then that light would be converging behind the retina. And if you're nearsighted, then that light would be converging before it reaches your retina. Okay, so you need some kind of glasses to correct that. Defects of lenses, aberrations. There are different kinds of aberrations. Spherical aberration, chromatic aberration. I want to look at chromatic aberration because I have a fun story about this. Chromatic aberration is this idea that, remember how different wavelengths of light actually refract at different angles? Well, that means that the colors will kind of spread out, wouldn't they? Right. So if you're using a refractive lens to do any of this magnification stuff, yeah, it's going to be a little fuzzy in terms of the colors. Right? Isaac Newton realized this, and Isaac Newton actually invented his own kind of telescope. So instead of having a couple of refractive lenses, Isaac Newton actually used a mirror, because if you use a mirror, like a reflective surface, then you don't get this chromatic aberration. Yeah, so if you ever use a telescope that involves like a reflective mirror, that was actually Isaac Newton's idea. Make sure I'm getting everything on the list. Okay, got that. Okay, diffraction and interference. Right, so we're looking at reflection and refraction, so different ways that you can bend light or cause it to change direction. Here's a different way that light can change direction, is diffraction. So this would be like light going around a corner. Here we go. Right. Like going around a bend, going around a corner, going around an object, and then depending on the relationship between the wavelength and the size of the object, you can get different results. Right? So that's what they're saying here. Practicing these pictures. Okay. Go back to there's something called Huygens principle, which is this idea that say you see like a wavefront emerging, like maybe something like this, right? You got a slit, you got some ripples going through. Remember I had that ripple tank, and you guys saw some patterns, somewhere to the side. Okay. Well, from a single point, this wave pattern would emerge. It looks like kind of circular. Right? From a whole line, it looks more like linear. You guys saw some similar type stuff with the ripple tank. Right? But Huygens principle says that you can actually treat each individual point as sending out its own waves, and the aggregate effect might be something like a straight line if they're all like next to each other. So an idea there. Looking at different shadows. So if you have a wide open slit, you can have like a sharp shadow. If you have a narrow slit, you actually get maybe some of this a bit fuzzier. Now interference is this idea that, well, if you have a couple of different, well, you guys know what interference is, right? You get constructive and destructive interference, right? So if you have two different waves interfering with each other, you might get some kind of interference pattern. You guys see where it's like dark light, dark light, dark light. Ooh, that's called an interference pattern, isn't it? I see some interference patterns for these too. Okay, oh yeah, there you go. Where if it's constructive, it'll be light. If it's destructive, it'll be dark. So there's this really famous experiment called the double slit experiment. Scientist named Young, something Young, you should know. Okay. But take a card, cut a couple slits in it. Actually, do I have your scissors here? You try this in real life. Okay. And there should be an interference pattern. Now, what this experiment shows, this double slit experiment, for now anyway, is that it's evidence that light has wave-like properties, like light has properties of a wave. This was a debate for a long time in physics. Is light fundamentally a particle, or is light fundamentally a wave? And it sort of has properties of both, actually. Particle properties, you could, if you ever hear the term photon, that's using a particle model for a light. But this experiment right here, Young's double slit experiment, shows light having more like wave-type patterns. So I tried this last night and it got it to work all right. So see if this demo works equally well right here. So we have a light source, right? Got a double slit right here, got a light source. See if I can get the camera in a good spot where you can see some kind of interference pattern. Okay, so Get one more go with this. What if I do something like a slip real close? At least get it there. Part of the trick of this is if I get it to work, can I get it to work on the camera? Somewhere on the camera. Okay. Tell you what, if you want to try this yourself at home, yeah, I'm not sure a good angle where either the projection camera or the video camera can see this, but yeah, there's like a for some anyway, this animation right here, this picture, you can't get this back to work. Right? So this is evidence that light is a wave or has wave-like properties. It could be thought categorized that way because of this interference pattern. So interference pattern is a result of it's evidence of waves. Okay? Now, interestingly too, if you have, let's say you go back to a single slit, like a single narrow instead of a double, like what if you have a single, right? The narrower and narrower you make that slit, something like this, actually sometimes the wider the light landing on the page behind it's going to be. That experiment I just told you guys about is evidence of support for something called Heisenberg uncertainty principle. And this double slit experiment actually has a certain extension to it too that also involves quantum mechanics. So I might tell you guys about that. Maybe after you guys take the AP exam, this double slit experiment is going to come back because there's a really weird consequence of this in quantum mechanics. Oh, interference from thin films. You guys ever done something like this? Like put a thin film, say, over some surface, and if you pay real close attention, it'd be like light, dark, or something like this. Maybe like clean wrap or something. Why would that be? Well, that's because of interference too. So really thin film, the light reflects off slightly different surfaces, and if that wavelength happens to destructively interfere, that would be like dark. Okay? So you get some pattern like that. Iridescence. So same idea. This is also the idea of if you guys ever see something like this, like a puddle of gasoline somewhere, it looks all like rainbow colors, all shiny. Like, similar type idea, you've got refraction and reflection going on in there. I wanted to talk about. Okay, speaking of iridescence, let me flip the screen over. Which you guys, particular example I have lined up. It's this right here. Right? So some things in nature are a certain color for, well, kind of unexpected reasons. For example, a butterfly. Why is this butterfly blue? And it's a weird kind of blue, right? It's all like super like shiny, glossy looking blue. It's not because of any blue pigment. Like if you zoom down microscopically really close, actually it's not colored blue at all. It's actually a color because of this iridescent effect of, this is there's some nanotechnology we're doing nowadays. We're able to get similar type of effect. These ridges on the wings happen to be spaced out at some tiny number of nanometers, which corresponds to the like a wavelength of blue light. So you have these rays that interfere with each other and create these patterns that happen to correspond to a wavelength of blue light. Okay? So you perceive it as blue because of the physical structure of the material. Yeah, so again, nowadays we're able to create materials that don't have any blue themselves, but they're like this type shape down to the atomic level. And then we call that iridescence. Oh, you know what? Let's flip back over. Turn the screen back again. I also wanted to show you guys pinhole camera. Right. So what if you have, excuse Spanish, but try to do a fast version of this. Say like a really dark room, but like a single small hole of light. Well, the rays of light will just travel in a single direction. And the result is, got some examples here. They go into this motel room. Actually, I'm just going to mute this. Okay. Put up a sheet, make it super dark in here. Okay. Cut out a hole. Okay. They try different size ones throughout the video, but one image just shows up on there. Okay, so there's the outside world. Look at that. There's the image right there. Now they left the shutter open for a while so they could get a good exposure. Now they're making the hole smaller and smaller as they go throughout this, right? So they did 4, then 3, then 2 centimeter diameter. Now the smaller you make the hole, the sharper the image that you're going to get. The disadvantage of smaller, of course, is you get less light. So there's sort of a trade-off. There's probably some optimal size focus, right? Some of the first cameras, actually cameras in general work on this principle, but some of the first ones were just like these big boxes and basically what they did with their room, just a miniature version, and you put film material on the back that can save that image. Okay, so there you go. That is a pinhole camera. That's how that works. Pinhole camera. Then, wait a minute. Where we are. Oh, okay. Actually, that's about the end of this chapter. I talked about holograms here. So I was just going to play you guys a video demo for holograms. So yeah, back over. Screen again. Okay, now this one. All right, how do holograms work? I'm so sorry, guys.
Images that appear to follow you as you move, but they're actually completely flat 2D films, and yet they have motion parallax. That is, as you move your gaze, things in the foreground seem to shift faster than things in the background, and they give you a stereoscopic view. That is, you see 2 different images with each eye, which together create the perception of depth. 3D movies aren't even this 3D. They don't even have motion parallax. And that hologram of Tupac at Coachella, it wasn't even 3-dimensional in any way. I digress. So holograms need some really special properties to appear 3D. One is that they show different images depending on where you stand in front of the hologram. This is really unusual. Let's recall that when you look at a regular photograph, it looks the same no matter which way you look at it. What you're seeing when you look at the photo is a white light beam. White light is like a crowd of people. They're walking with different footstep lengths, like the different wavelengths or colors in white light, in every different direction as the light spreads out. That beam reflecting off the photo is like freeze framing the white light crowd. Blue light here, red light there, and it's stagnant. You can't move the crowd around. Blue parts will always be here to the left of those red parts. With a hologram, you can move. It provides that parallax effect. Check it out. This is the setup to make one type of hologram, although the other types are similar. It starts with a laser beam, which is split into 2. Then both of the beams go through lenses to make them spread out. One beam, the object beam, bounces off the object you're trying to image and shines onto the holographic film, while the other beam, the reference beam, goes straight there. And then, well, this is why we use lasers. Laser light looks very different from white light. It's all going in the same direction, it all has the same wavelength, and it's coherent, meaning all the light waves are in phase or in unison. This is so key to making holograms. In cases where 2 coherent laser beams meet, they can create regular striped interference patterns like this. In our case, the reference beam is a coherent beam, though the object beam is not. Still, when they meet, they also create an interference pattern, but a special one that encodes the specific 3D information about the object onto the holographic film. Now, we had a reference beam and an object beam, and together they created an interference pattern. A plus B equals C. What would happen if we took the interference pattern and sent the reference beam in through the back? That's kind of like C minus A. Well, that equals B. And sure enough, with this type of hologram, sending a laser beam in through the back of the film is how you get out the original object beam. That's the same beam that was created when the laser first shined off the object. Since this reproduced beam is a perfect copy of the object beam, you can't tell whether you're looking at the light from the hologram or from the original scene, complete with motion parallax and stereoscopic views. The other cool thing about holograms is that all parts of the hologram carry information about the object. So you could cut a little square of the hologram and you'd still be able to see the entire object in it. You can't do that with a photograph. Deep down though, the holographic film is just a bunch of interference patterns. Up close, the film looks like this. whereas a photographic film just looks like a smaller version of the image, much less cool. Oh, and the Tupac hologram, that was a stage trick called Pepper's Ghost that dates back as far as the 16th century. You could even create one at home. I'll link to some tutorials in the description.
Oh, speaking of which, Pepper's Ghost, this is one that's used at Disney parks a bit, so take a look at that.
Today, I'm going to show you how to make the Pepper's Ghost illusion. It's an old special effects technique for creating transparent ghostly images. It works by reflecting the image of a ghost off a clear material such as plexiglass. The ghost is located off to one side where it's out of view. The plexiglass is set at a 45-degree angle to both the audience and the ghost. At this angle, the background remains clearly visible, but the plexiglass also partially reflects an image of the ghost. To the audience, it looks like there's a transparent ghost in the scene in front of them. It's pretty simple. So now I'm going to show you some ways that you can implement this technique. The simplest way to apply it is in photographs and video. Start by setting up your camera on a tripod. Then position your ghost to one side of the camera. The ghost can be a person, a computer monitor, or just a paper cutout. Hold up the plexiglass at a 45-degree angle to the camera and the ghost. The camera should see a faint reflection of the ghost. You may also get reflections of other objects around the ghost. To avoid this, you can set up your ghost in front of a black backdrop. This is a really easy way to make ghost pictures, and it doesn't require any editing software. Creating a Pepper's Ghost illusion for a live audience is a little more difficult. The easiest example is making a ghost appear in a window. First, you need a large sheet of plexiglass. Then you need a way to prop it up behind the window. To do this, I put a table underneath the window, and I added sheets of cardboard to it to make a surface that's level with the windowsill. I propped up the plexiglass in the corner of the window. I also added a small clamp to help hold it in place. Then I positioned the ghost to the side of the window just out of view. You need the room to be dark so that the edges of the plexiglass won't be visible. In this case, you don't need a black backdrop, but you do need to use a flashlight to help illuminate the ghost. The result is a transparent figure in the window that stares at people as they walk by your house. Creating a ghost in a doorway uses basically the same procedure, but because the opening is much larger, you need a much larger sheet of plexiglass. Well, that's how to make Pepper's Ghost. Try it out.
Yeah, so look for that next time, huh? Might see this somewhere around. Let's look at
Hi again.
all right, so Venom's wheel. Right, so this one I just passed out to you guys. This template explains this for a while, but he's making a point that like color doesn't really exist. It's actually something that it's just something your brain interprets different wavelengths of light. And as a demo, Spence's, you guys see this wheel is just black and white, right? But it's got these stripes of different colors, and it gives us a spin. Some people can see the colors better than others. So I mean, we all perceive the world a little bit differently. We all have a little bit different senses, a little bit different brains for all individuals. So what I see is, looks like the inner stripes are like violet, then kind of red, then kind of yellow, then kind of green. Actually, curious, how many of you guys see what I see? See those colors?
I see like violet.
I see
Okay. Yeah.
I see the violet.
I see the violet the most, and then the outer one looks orange.
Okay, I can kind of see it. Like kind of red orange, sort of. Yeah. To me, this looks kind of gold. This looks kind of.
The middle tone is really light.
And this might work at different speeds too. So sometimes if you speed up faster. Oh, there you go. Okay. Okay. You guys want to try this out? See if it works in. Really? Because sometimes there's an effect of like if you play something on a video, because of certain like framework rates, it could have a slightly different effect. So let's switch back over. This. So I passed out to you guys this template. You guys got some scissors, so go ahead and cut out. Now what I did for the central axis is I just took a pen and punched through where the center point would be. So it looks like this, right? And then just to some of this margin scrap paper, actually only took a little tiny rectangle about half this length and a little width, so rectangle about this big, and wrapped it into a circle, and then stick it through for the central axis. Now, you guys remember back from rotational dynamics, think about how things are going to rotate. You're basically making a top here, right? Like a top. That if you have a central axis that's extremely massive or extremely tall, or a combination of those, this is probably not going to be very stable. It's probably going to be hard to spin. But if a lot of your mass is on the paper itself, let's say in proportion to your axis, it's probably easier to spin. So that's why I cut just a small rectangle just to, all right. Okay. All right. So give us a spin, got to work this morning. We're gonna find out. Ooh, yeah. And I see in front of me, I don't know, see if it works on camera. In front of my face anyway, I'm seeing some colors emerge from these stripes. That's fun, really well stuff on the screen. Yeah. Right, so I'm seeing the colors work really well in front of me, so you guys gotta try that too.
What did you find the middle?
Okay, the middle is, see where, okay, there's obviously this center line between the black and the white, okay, but also, see it's like an imaginary line that goes like this way, and you guys might have like straight edges on your desk, possibly a ruler or protractor.
What did you put like inside the middle?
Okay. So I did this. I just can I borrow your scissors? All right, so you might have like a margin like this. I just chop this in half so that it's not super massive. Okay. Then line this around like this. So this could act as a central axis, like that. Okay. Then take a pen and put a, like right there, that would be the center point. Let me zoom in so you guys can see exactly the center point. Okay. I'm taking it right about here. See where like there's like a line that you extrapolate right about there. You guys think that looks like the center point? Okay. So then push a pen right there. Point. Okay. And then take your central axis. Go on in there. Okay. And then it'll look like this. Yeah. All right. See what else I have. Oh, okay. So this was an ambitious list, but I got through that. So I do have some other stuff lined up. Let's do some mirror puzzles, and then I'll have you guys a femto camera where you guys can watch a bullet of light travel across the room. Let's do some mirror puzzles. So this one, we got this lady standing in front of a mirror that's 1 meter away from her, right? And say she's got this flower on her head. Let's say it's kind of on the back of her head where she can't really see it or see it in front of the main mirror, but she's also holding this handheld mirror. Okay. So what she's doing, she's looking into the big mirror and seeing a reflection of this flower on her head. And the question is, how far in the back of the dresser mirror does she see the image of the flower? Guys, a minute, think about that. Right. So when she looks in this dresser mirror, how far behind that does she see the flower? Give you guys a multiple choice. Let's say either 1 meter, 1.5 meters, or 2 meters. Who says behind the dresser mirror, it's going to be 1 meter? Who says 1 meter? No, nobody says that. Does anybody say 1.5 meters? Does anybody say 2 meters? 2 meters says that. Okay, yeah, so you guys figured this out. Because she's looking at the reflection of her reflection. Wouldn't the initial reflection be 1/2 meter behind the handheld mirror? So it'd be like right about here, right? So imagine there's a flower right here. I forgot one printout, otherwise I would draw a little flower right here. Okay. And then since she's looking in the dresser mirror, she's seeing a reflection of that reflection. Well, the handheld reflection is effectively 2 meters from the dresser mirror. So its reflection is going to show up 2 meters on the other side. And so it looks like a 2 meter distance here. Okay. Oh, this next question I like a lot. How large a mirror would you have to see your full height? Because I know if I have a little tiny like handheld mirror, right? Like this one right here. This is not big enough to see your full like person. Okay? If you had like a whole glass wall in front of you, or like this guy, you know, the mirror is bigger than he is, that's plenty big enough for you. You can see his whole self. But what's like the minimum size of a mirror that you would have to be able to see yourself? I'm just gonna take, this is one of those problems that's really fun to think really deeply about, but I'm just gonna sort of give you guys the answer here. Okay, so this was stick figures. Let's say this guy's got this dresser mirror like this. Okay. Now, would this guy's reflection be same size on the opposite side because it's just a plain mirror, right? A plain like a flat mirror. Okay. So here's like object, image, approximately. So like that. They're supposed to be the same height. Give them a floor here, and the ceiling about, supposed to be the same height. So how much mirror does he actually need to see his whole self? Does it depend anything on this distance to the mirror? It turns out it doesn't, and I'll show you guys why. So if he's looking at the mirror, where does he see the top of his head? Like here's his eyeball looking, right? And his eyeball at the back of him. Give him a couple of eyes. That's creepy. So he's looking with his eyes, seeing the top of his head. It appears to be like in this direction, right? But that light ray is actually the boing bouncing off the mirror from here. So there's a light ray going boing, and if you extrapolate backwards, maybe I should dash everything. Maybe everything to the right of the plane, I should actually dash. He's extrapolating back saying, okay, that's the top of my head. Then he's looking down and he sees his feet. And so here's his feet down here. So there's a light ray that boing, extrapolate backwards. Looks like it came from back here. But really that came from boing, something like this. Okay? Remember the whole, here's the normal line to the mirror, and angle of incidence matches angle of refraction. The whole law of reflection, right? Yeah, angle of incidence matches angle of reflection. Oh, so do you guys see that he could see his entire reflection in just this here piece of the mirror right here? Huh, and what is this compared to his full height? Well, let's do a measurement. So he's actually, it looks like about a little shy of 6 centimeters tall. How big is this? 3 centimeters. Ooh, so this is 6 centimeters from here to here. We got 6 centimeters. And this height right here is only 3 centimeters. Huh. Okay, so the answer is that to see your full self, you only need a mirror that's half of your own height. And again, it doesn't matter if he's close to the mirror or far away, that's always gonna be true. Now the catch is that you have to have it positioned exactly in a place where you can see it, right? Because if you shift it down or up too much, then you won't be able to see your full self. Okay. Try this next time you guys are in front of a reflective surface. Let's say you're inside, I know I've been inside an airport terminal before. There was like a big glass wall. It was night outside, so it worked kind of reflective surface. Notice where your head is, top of your head, and where the bottom of your feet are. And maybe you could like either make a small mark on the wall or just a mental note of where that is, or maybe some reference point. And as you back up further away or get closer to the surface, the location of your feet on the reflection surface and the location at the top of your head or the location of anything else actually does not move. It actually stays in the exact same spot. And that height ends up being half of your actual height. That's fun on that. Okay. This next question, she's looking at this handheld mirror, and let's say she's like, I want to see more of my face. I want to see a little bit of my face. How can I see more of my face? So should you hold the mirror closer, further away, or is not helpful at all? Well, it's the same principle as what we were just looking at here. So remember, getting closer or further away doesn't change the amount of mirror that you need to see your image. So to see more of her face, the only way to do it is she needs a bigger mirror. Okay, that's the only way. Okay, holding it closer or further away actually doesn't change it. Where's my... Yeah, if you guys ever get your hands on that handheld mirror, you can try that too. Right, so closer, further away, the amount of your face you see actually does not change. Right. Right, just for completion, got one more question. These are all questions from Paul Hewitt materials, by the way. Paul Hewitt drew all of these pictures. And so this last one, say you take a picture, this bridge, which is the realistic image. You guys see it has to be the one on the right. Almost everybody gets this question right because the reflected shadow you can see underneath. Okay, so that's fun too. Okay. All right, last thing today. Does anybody got any questions about anything so far? Tomorrow I'll have an FRQ lined up for you guys because I covered pretty much all the demos I think I wanted to cover. All right, I got a real showstopper here called Femto Camera. So we're trying to watch about half of this, but so this guy looks at the history of like slow-mo photography. It's the 1960s. There's a bullet going through an apple. But femto photography, this works a little bit differently. There's a bunch of, well, sorry, he's explaining the technology behind this, but I want you guys to, this is the small time we have left, to watch this bullet of light actually go across this. Now, if you slow this down to, here. Okay, so bullet of light going across this Coke bottle. Now this takes, notice it's been slowed down by a factor of 1 billion, right? Factor of 1 billion. Okay. I want to say in part of the part that I skipped, if this was a bullet traveling across, something like that, and you slow it down by a factor of 10 billion like that, it would take like a whole day to watch it or something like that. Yeah.
Now remember, the whole event is effectively taking place in less than a nanosecond. That's how much time it takes for light to travel. But I'm slowing down in this video by a factor of 10 billion so you can see the light in motion. But Coca-Cola did not sponsor this research. Now, there's a lot going on in this movie. So let me break this down and show you what's going on. So the pulse enters the bottle, our bullet, with a packet of photons. They start traveling through and they start scattering inside. Some of the light leaks, goes on the table, and you start seeing these ripples of waves. Many of the photons eventually reach the cap and then they explode in various directions. As you can see, there's a bubble of air and it's bouncing around inside. Meanwhile, the ripples are traveling on the table. And because of the reflections at the top, you'll see at the back of the bottle, after several frames, the reflections are focused. Now, if you take an ordinary bullet and let it go the same distance and slow down the video again by a factor of 10 billion, do you know how long you'll have to sit here to watch that movie? A day, a week, actually a whole year.
Oh, whole year.
It'll be a very boring movie of a slow, ordinary bullet in motion. And what about some still life photography? You can watch the ripples again, washing over the table, the tomato, and the wall in the back. It's like throwing a stone in a pond of water. By the way, this is how nature paints a photo, one femto frame at a time. But of course, our eye sees an integral composite. But if you look at this tomato one more time, you will notice as the light washes over the tomato, it continues to glow. It doesn't become dark. Why is that? Because the tomato is actually ripe and the light is bouncing around inside the tomato and it comes out after several trillionths of a second. So in the future, when this femto camera is in your camera phone, you might be able to go to a supermarket and check if the fruit is ripe without actually touching it.
Technology application.
So how did my team at MIT create this camera? Now, as photographers, you know, if you take a short exposure photo, you get very little light. But we're going to go 1 billion times faster than your shortest exposure. So you're going to get hardly any light. So what we do is we send that bullet, those packet of photons, millions of times and record again and again with very clever synchronization. And from the gigabytes of data, we computationally weave together to create those femto videos I showed you. And we can take all that raw data and treat it in very interesting ways. So Superman can fly. Some other heroes can become invisible. But what about a new power for a future superhero? To see around corners. The idea is that we're going to shine some light on the door. It's going to bounce, go inside the room. Some of that are going to reflect back on the door and then back to the camera. And we're going to exploit this multiple bounces of light. And it's not science fiction. We have actually built it. On the left, you see our femto camera. There's a mannequin hidden behind a wall, and we're going to bounce light off the door. So after our paper was published in Nature Communication, it was highlighted by nature.com, and they created this animation. We're going to fire those bullets of light, and they're going to hit this wall. And because of the packet of the photons, they will scatter in all the directions, and some of them will reach our hidden mannequin, which in turn will again scatter that light. And again, in turn, the door will reflect some of that scattered light. And a tiny fraction of the photons will actually come back to the camera, but most interestingly, they will all arrive at a slightly different time slot. And because we have a camera.
Oh, see the result of this thing. Ah, there it is. Aha, look at that. All right, you guys have a good Thursday.